the air standard OTTO cycle. The air standard OTTO cycle is an ideal cycle that approximates a spark ignition internal combustion engine. Internal combustion engine. OTTO cycle. A spark ignition internal combustion engine. This cycle is shown on PV and TS diagram in this picture. Process 1-2 is an isentropic compression. 1-2 second. Isentropic. Compression of air as the piston moves from bottom dead center to the top dead center. Top dead center. As shown here, we have an increase to pressure. There is constant bottom dead center to top dead center. Heat is then added at constant volume with the piston is momentarily at rest at top dead center. This process corresponds to the ignition of the fuel-air mixture process by the spark and that substance burning in the actual engine. Process 3-4 is an isentropic expansion also. So heat is added to the combustion phenomenon at V constant. 2, 3 and 4. 3-4 is isentropic expansion, top dead center to bottom dead center. And process 4-1 is a rejection of heat from the air. 4-1 rejection of the heat to the air. While the piston is at bottom dead center. QA. PV diagrams are also available. The thermal efficiency of this cycle is found as follows. Thermal efficiency is W net on QH. QH minus QL on QH. And for an ideal gas, eta Cv at constant value T4 minus T1, this process QL N and MCV T3 minus T2, this process QH. Or we can have eta equals to T1 T4 on T1 minus 1 T2 T3 on T2 minus 1. Note that in isotropic process T3 on T4 T3 on T2 T4 on T1. Consider this picture again for the temperature realize T4 T3 on T2 T4 on T1. And eta thermal also can be written as this. And RV is compression ratio. We can conclude that from this relation, the efficiency of the air standard Otto cycle is a function only of the compression ratio function of RV compression ratio, and that the efficiency is increased by increasing the compression ratio. The figure here provides a picture of the various This figure shows a plot of the air standard thermal efficiency versus compression ratio as shown in the picture. Eta and compression ratio. It's also true that the efficiency of actual spark engine can be increased by increasing the compression ratio. The trend toward higher compression ratio is promoted by the effort to obtain higher thermal efficiency. In the actual engine, there is an increased tendency for the fuel to denote as the compression ratio is increased. After detonation, the fuel burns rapidly and a strong pressure base present in the cylinder gives rise to the so-called spark knock. Therefore, the maximum compression ratio that can be used is fixed by the fact that detonation must be avoided. Advances over the years in compression ratios in actual engines were originally made possible by developing fuel with better anti-knock characteristics, primarily through the addition of tetra-T lead. More recently, however, non-leaded gasoline with good anti-knock characteristics have been developed in an effort to reduce atmospheric contamination. Some of the most important ways in which the actual open-cycle spark ignition engine deviates from the air standard cycle are as zero, the actual actual open-cycle spark ignition engine, deviate from the air standard cycles. Are the first one, the specific heat of the actual gases, increase with an increase in temperature. The combustion process replaces the heat transfer. Replaces the heat transfer. At high temperature. And combustion may be incomplete. Each mechanical cycle of the engine involves an inlet and an exhaust process. And because of the pressure drop, through the valve, a certain amount of work is required to change the cylinder. With air and exhaust, the products of combustion. There is considerable heat transfer between the gases in the cylinder and the cylinder wall. And the last one, there are irreversibilities associated with pressure and temperature gradient. And temperature gradient. The next section is the diesel cycle.